Let's talk about polynomials in this lecture. When we looked at integers like say 324 in the expanded form, we wrote it in this format. We said 3 times 10 squared plus 2 times 10 plus 4 times 10 to the 0. And we said that the numbers 3, 2, and 4 are called the coefficients. 3 is the coefficient of 100 or 10 squared, 2 is the coefficient of 10 to the 1, and 4 is the coefficient of 10 to the 0. We said before how if you replace the base 10 with x's, you end up with examples of polynomial. So replacing base 10 with x, that's considered playing, right? Because we already have something and we want to replace pieces of it to see what will happen just for fun. So 10 is replaced with x's, and we have an example of a polynomial, 3x squared plus 2x plus 4. To have any generic polynomial in one variable, you can also change the coefficients. We're not restricted to just integers. You can replace the 3, 2, and 4 with real numbers, and then you have a different polynomial. So again, we have 3.4x squared plus square root 2x plus 1/4. That's an example of a polynomial. The highest exponent on the variable is called the degree of the polynomial in one variable. So degree of the polynomial in one variable is the highest power that occurs in all of the terms that you see here added together. So let's take a look at some definitions. A monomial is a product of real numbers and variables to whole number exponents. The real numbers are called the coefficient of the monomial, and the sum of all exponents in the variable terms is called the degree of the monomial. So let's take some examples. Here we have square root 2x to the 100. So the degree of that monomial is 100. The degree of this monomial is 5 because that's the power of exponent. If you have a term with multiple variables, then to compute its degree, you look at all the exponents involved on the variables and take their sum. So here the degree of this monomial is going to be 8 because 3 plus 5. Those terms that you see, square root 2, negative 5.34, negative 2 over 2,345 are all coefficients of the monomial. All right, so now let's take a look at polynomial. A polynomial is a finite sum of monomials. That is addition of one or more monomials. And so the degree of a polynomial is the highest degree across all the monomials in the polynomial. So here we have a polynomial, and you can see that the degree of that polynomial is 100 because if you look at each term, 100 is the highest exponent in the terms that are being added. The numbers square root 2, 5, negative 4, 15 are called coefficients of the polynomial. If you look at an example of a multivariable polynomial, then we have to find the degree by looking at all the monomial terms, looking at its degree. So for example, the monomial here, what do you think its degree is? Why don't you think about it? So that degree is good, 12 because 10 plus 2. The degree here is going to be 2 plus 4, 6. Here it's going to be 1 plus 1, 2. So the highest degree of that, the highest degree monomial is this one. And so the degree of this polynomial is going to be 12. The coefficients are negative 34, a 5, and a negative 4.1. Those are the coefficients of that polynomial. You can also have polynomial with complex numbers for coefficients. So you're not just restricted to real numbers. So you can pretty much have whatever you want for coefficients, and the degree still is the same. Addition of all the exponent terms in each monomial, and then the highest power. So why don't you see if you can find the degree of this polynomial. So here we have 1 and 3, so 4, 7, and here we have 7 plus 3, 10. So this is the highest degree monomial. So the degree of this polynomial is going to be 10. An algebraic term is a product of numbers and variables using any algebraic operation. So you can have addition, subtraction, multiplication, division. You can also have any kind of exponents. You are not restricted to just whole number exponents like you are in polynomials and monomials. So here's some examples. This is an example of an algebraic term because we have a numerator and we have a denominator. Such a term is actually called a rational expression. It's not a polynomial because the variable appears in the denominator. And here are two examples of algebraic expressions that are not polynomials. You can see here we have a variable term in the denominator. Here we have a integer exponent, a negative exponent, and that's not allowed for polynomials because you need whole number exponents. Okay, how about this one? This is a polynomial because you have coefficients and you have variables raised to whole number power. So that one is an algebraic expression that's also a polynomial. So a polynomial is a special case of algebraic expression. So let's just do some practice problem. Pause the video, do the problems on your own so you can see if you're getting it. So is the first one a polynomial or not? Go ahead and think. Pause. Assuming you have paused and come back, here's the first answer. First one is not a polynomial because you have square root x, which is the same as x raised to a half power, which is not a whole number power. All right, how about this one? No, because of x squared is in the denominator. Can't have variable terms in the denominator. Same thing, same reason applies here. You must be able to reason out why something is a polynomial and why something is not a polynomial. Here, it's not a polynomial because this x is an exponent. Remember, you can only have whole number exponents. So it's an algebraic expression, but not polynomial. Homework? See what you can do. So in general, there are times when we would like to refer to polynomials, generic polynomials that represent all types of polynomials. So let's just start with a degree 2 polynomial in one variable. So 2x squared plus 3x plus 5. However, what if I wanted to think about all degree 2 polynomials in the second degree? Then I would have to write it like this. So we would have ax squared plus bx plus c as a polynomial of degree 2. A, b, and c are real numbers, so this is how any degree 2 polynomial would look like. So you can see the problem now that we're going to run into. If you have more than 26 terms, then what? You're going to run out of letters. So to fix the problem, mathematicians have come up with an ingenious solution. Look, we can start with powers of x's here. So we can have constant term, which is when there is no x term. Then we have x to power 1 term, x to power 2 term, and so on. The dot, dot, dot means you just continue like that, how many ever terms you have. The generic coefficient then is represented by a variable a with a subscript n. So a sub n is a number that would be the coefficient of x to the power n. So for example, a sub 2 is a number that will be sitting in front of the x squared term. A sub 1 is the number that sits in front of the x term. All right, so basically we create infinitely many variables now. We'll never run out of variables because we know there are infinitely many counting numbers. So this is a great way to represent any generic polynomial of degree n. A sub k is referred to as the coefficient of x to the k. Remember, coefficient just means that it's a number like 4 or 4.5 or square root of 2. It's a real number. So for example, if we have 9x to the 5th minus 3x to the 4th plus 2 in this format, all that means is that a sub 5, which is the coefficient of degree 5, is 9. Coefficient of degree 4 is negative 3. And then the coefficients of third degree, second degree, first degree are all 0, so that's why they're missing. And then the constant term a sub 0 is 2, which is the last term with no x in it. That's referred to as a constant term. The use of subscripts on coefficients is a clever way to not run out of symbols. So polynomials are used in physics, chemistry, business, lots of other disciplines, and the polynomials that we use frequently are given names, so you get familiar with these names, which will help you later to recognize them.